so here, there is asking you also to figure out p-value. P-value is the same as the concept of p-value is something that we're going to compare with alpha. So p-value is going to be the value of alpha. P-value is the value of alpha that will change the conclusion of the test completely, reverse it, okay? So in my example that I had, I erased it, okay? So I had null hypothesis, mu equal 16, and alternate hypothesis, mu equal, not equal to 16. So with alpha of 1%, and test statistic for me was 1. This is the exercise, not the practice one, but the exercise one that I went over on page 262? 242. Okay, page, okay, exercise 1, page 242, okay. So, and the graph looked like this one. So Z, and I had 2.75, the critical value was 2.575, and two critical values negative 2.575, and my test statistic was 1. I'm sorry, test statistic, TS equal 1. Okay, this is my example. And what happens is that usually for two-tailed test, we put half of the alpha here, alpha over 2, which is 0.01 over 2, which is 0.005, and half of the alpha on upper tail. If it's a two-tail, okay, upper, lower, okay, half of the alpha, which is 0.01 plus 0.005, and we put confidence 99% in the middle. Okay. Now, the concept of p-value is like this. We are going to figure out, the highest alpha for which the result of the test, and remember for my test, step 5, I did not, do not reject null hypothesis. My conclusion was that do not reject null hypothesis. Okay. So here, p-value is the highest alpha for which the result of the test either will not change or change completely. Okay, there's a borderline. Okay, so basically p-value. For instance, if I were to choose rather than alpha of 1%, if I had chosen in the beginning alpha of 5%. Okay, so let's do with the green ones. If I chose alpha of 5% instead of 1%, okay, then for alpha 5%, critical values would have been plus or minus 1.96. Okay, so for alpha of 5%, it would have been 1.96. Critical value would be 1.96 and negative 1.96. Okay. If I had chosen alpha 5%, what would have been the conclusion? Still the same conclusion. Do not reject, because I am still within the acceptance region. Right? Everybody follows this? Okay. If I had chosen okay, alpha of 10%, then critical values would have been plus or minus 1.645. Critical values would have been 1.645. I want to choose a different color so that you know, so here, let's use red here. I don't have red there. So if I chose alpha of 10%, critical values would have been plus or minus 1.645. Okay, so 1.645 would have been here approximately. Okay, critical value plus 1.645, and here critical value minus 1.645. Okay, what would have been if I had chosen alpha of 1% or 5% or 10%? There is absolutely no change in the conclusion, because in all three cases, the statistic is within this acceptance region, this green acceptance region, and this black acceptance region. So absolutely no change. So the idea of p-value is that to find the highest alpha that would change the conclusion completely from do not reject to reject. So in order to find alpha, what we do is that we find the value the area under the normal curve, in this example, to the right of the statistic. So p-value, this doesn't make sense. I wanted to have a different color, but it doesn't work. So p-value is equal to probability that z is greater than 1, greater or equal to 1. Okay, so probability that z is greater than 1, namely this area, this dotted area, the entire dotted area. Okay, if I calculate this one, so it's going to be probability that z is greater than 1 is 0.5. I don't have this dotted area, but I have this area, which is 0 to 1. So if I subtract this area from 0.5, I get this dotted area. It's going to be 0.5 minus probability that z is between 0 and 1, which is 0.5 minus 0.1334. 36. What is it? 3. What is it?
3413.
34? 13. Okay, correct. So correct. 1587. Correct. Approximately 16%. So this one tells me that if from the beginning, had I chosen alpha up to about 16%, let's say approximately 16%, the result of the test would not have changed. As soon as I change an alpha greater than this value, the result of the test will be completely changed from do not reject to reject. Everybody sees that? Yes.
Sorry, where does the 0.3413 come from?
Okay, this is probability that z is between 0 and 1. It's this area. This area.
Oh, okay.
This area. Okay. So p-value is going to be a value of alpha that will completely reverse this result of the test. Whatever it is, it will turn it around, completely reverse it. Okay. So if you go to page,
Isn't it 2 times
Okay, so this one, if it's a two-tail test, so it's going to be, you're absolutely right. So it's going to be 1 and 1. There are 2 of them. So here, there's going to be another one here. Okay, so it's going to be probability that z is greater than 1 plus probability that z is less than 1, less than -1. And it will be 2 times, because it's perfectly symmetrical, it's going to be 2 times this, 2 times this. It's going to be plus 1587. So the result is going to be 3174, approximately 32%. So it's going to be this area plus this area. Thank you, Sam. I owe you 2 half a points. Okay, so far. Okay, so far. Thank you. Good catch. Okay, so why don't you go ahead and go to your exercise on page 243, I believe, and see whether now you can answer parts D, E, F, and G. I think they're all D. Okay, to calculate p-value, refer to book page 238. In the middle of the page, there are some guidelines for you how to calculate p-value for two-tail test, upper tail, lower tail. Okay. Middle of the page in yellow highlighted boxes. Okay, so p-value for two-tailed, upper tail, and lower tail. So information on middle of page 238 in the yellow highlighted boxes, there are 3 boxes, will tell you how to calculate p-value for two-tail, upper tail, lower tail test. For upper tail, lower tail, and two-tail. It's right there. Okay. So now that we have learned this concept, let's go to the next test, which is making inferences about population mean mu when standard deviation of the population is not known. Okay, so that's second test. Test number 2. Okay. Test of hypothesis regarding single mu. Okay, this is one sample, single mu, and population mean mu, no difference. Okay, just single mu. When population standard deviation sigma is not known. Okay. Everything that we learned on the first test is true. The only difference is going to be Now, because population standard deviation is not known, we cannot use Z table. We're going to go to T table. So that's one difference. And test statistic is going to be X bar sample mean minus mu sub 0, which is the hypothesized value of mu under null hypothesis, divided by S over square root of n. Because sigma is not known, we are going to substitute for sigma its best estimate, which is sample standard deviation. And the decision-making rule is going to be like this. Instead of Z, we are going to have T. And depending on whether we have two-sided or one-sided upper tail, lower tail, then the critical value. If we have two-sided, okay. Remember that remember that last time that we talked about T-table, we said they're two-sided on top row and one-sided. And for chapter 9, I said forget about one-sided. In chapter 10, we are going to either use two-sided or one-sided. Two-sided is for putting alpha on both ends or both tails. And one-sided will be the one that's an upper tail or lower tail. Okay, so it's going to be like this. Upper tail, we're going to put all of the alpha here, and for lower tail, we're going to put all of the alpha in the lower tail. So two-sided, one-sided, either upper tail, lower tail, okay. And the table, the T-table has provision for two-sided and one-sided. So we're going to use that. So let me give you an example. Let me go over the exercise 2 on page, what's the page? 247. Okay, so it's going to be exercise 2 on page 247. So I'm going to, why don't you read the paragraph of exercise 2 on page 247, then I'm going to go over it, and then you do a practice in class. We have enough time for you to do a practice in class. Okay. So exercise 2, page 247. So here it says that life expectancy of light bulbs distributed normally with population of 1405. So X is a random variable which is life expectancy of light bulbs, okay, and has a distribution which is normal. We mean 1405 and standard deviation, which is unknown. We don't know the standard deviation, okay. So we'll put just sigma here. We don't know. Now, what happens is that this manufacturer recently modified these light bulbs in hope of increasing life expectancy. Okay, they did some changes in manufacturing, in material, and this and that, in engineering, so that they want to make sure that they get life expectancy of more than 1405. Okay. So after they implemented the changes and new technology and new material and new engineering, they took a sample of size 25 of this new updated light bulbs, and they calculated the sample mean, which is 1411, sample mean, X bar, 1,411 hours, okay, or days, I think days, okay, yeah, hours, okay. With the sample standard deviation of 12.0385. S, 12.0385. And now, we are going to conduct a test using 1% level of significance, alpha 1%, does the evidence suggest that the modification increased? That's the point, that's a key point, okay? Whether this modification of what increased, that's a key word, the mean life expectancy. Okay, so null hypothesis and alternative hypothesis here. Okay. First, we want to make sure that this one has, okay, so mu, we want to make sure that mu is not greater than 1405. It used to be 1405. With the modification, we're hoping that it's above 1405, okay? And because there is no equal sign here, this is going to be alternative hypothesis. And therefore, null hypothesis is going to be mu less than or equal to 1405. That's how you analyze and formulate null and alternative hypothesis. The key word is that whether the modification of white light bulbs increased life expectancy from 1405. So this is going to be our new hypothesis. Mu greater than 1405, and because it does not have equal sign, it will be alternative hypothesis, and hence null hypothesis is going to be whatever this is not, which is less than or equal to. Everybody okay with this analysis? Okay, so then alpha, I think, is a 1%?
Yes.
Yes, alpha 1%. So this is step one. Step two, alpha of 1%. Is this upper tail, lower tail, or two-tail test? Which one? Upper tail. Why? Okay, the direction. Look at the direction of inequality in alternative hypothesis. It's pointing to the right, pointing to the upper tail of the distribution. Okay, so it's the upper tail. Okay. So it's a one-sided or two-sided. Upper tail is one-sided, one-sided. So this is also one-sided. Therefore, one-sided. Then we go to the t-table and look for, and by the way, what is degrees of freedom in t-table?
24.
Why 24, Sam, correct?
N minus 1.
N minus 1. 25 minus 1 is 24. So we go to t-table, concentrate on row of degrees of freedom 24, and then read across until we get to one-sided 99%. One-sided 99%. So T of one-sided alpha of 1% and degrees of freedom of 24 is equal to what? Go ahead and find it on the t table. 2.492. Okay, everybody sees this one? Everybody can see this 2.492 in the t table. Camille, you're not? Can you see that in the t table? Okay, so go to t table. Concentrate on the row 24, degrees of freedom, and then the intersection of this row and the one-sided 99%. This one. Okay. Oh, you don't see it, you want. Okay, you see that one? You see that one? Okay. Chen, you see? Fergus, you see that one in t-table? Chen? Okay. Okay. Maya, you see that one? Okay. Hugo, everybody there, we all went. Okay. Alex, you see that one in the t-table?
About to.
Okay, not yet. So go to t-table, concentrate on row 24, and then one-sided 99%. So one-sided row 99% intersection of this column and that row. Okay, Julia, you see it? Kevin? Shem, you okay? Sam, you said Juan, you said? Okay, good. So That's one of the differences. Is instead of using Z table, we're going to use T table. And because this is upper tail test, and then we're going to calculate test statistic as well, and then after that we're going to choose a guideline for inverse making. So step 3. The statistic is going to be x bar minus mu naught over s over square root of n. So it's going to be 1411, 1411 minus 1405 divided by s, which is 12.0385 divided by square root of 25. And this happened to be equal to and 2.492. 2.492. Test statistic is 2.492. So is the critical value. This is critical value. It happened once in a blue moon. Okay, it happened very, very rarely that these two are the same. I intentionally made the calculation so that they are the same, just in case some student, thinks of what will happen if they are the same. Okay. Oftentimes they're going to be different. Most of the time, like 99.9999 is going to be different. Once in a blue moon, it will be the same. So step 4. Okay, so draw the T distribution, which is like normal distribution. Okay, and this is upper tail and critical. There's only one critical value at 2.492. And what it happened that test statistic also is the same. When this happens, which is rarely happen, we call it test inconclusive. We don't know what the result is. No, neither we're going to reject nor accept. Okay, no hypothesis. So what is the next step? If this happens and you are the research analyst, what would you do after that? If this happens, the test statistic and critical value are the same.
It's inconclusive.
Inconclusive. So what is the next step?
One more samples.
I'm sorry?
Or run a bigger sample. You'll gather more data.
Exactly. You go out and gather more data. Maybe instead of 25, make it 50. Go to higher sample size and see whether with the higher sample size you will get a conclusive result. Thank you. Okay, so in this example, when this happens, alpha and p-value are the same. It's the same thing. Okay, so if you're asked to calculate p-value, the p-value is going to be the same. Basically, it's going to be at 1%. Okay, now we have 15 minutes for you to do practice number 2, which is on next page, on page 248. Go ahead and see whether you can do, okay. Calculation of p-value using t-table is a little bit involved here. So if you are not able to calculate the p-value for practice 2, it's okay. I'll teach you. I'll teach you how to. So mu x is life expectancy of computer batteries, which has a distribution of normal distribution with mean 13.5, and sigma, which is not known, so n equal 20, and then, and then 20, which is 13, 11, and standard deviation 12 at 5%. Okay, so modification increased. The keyword is increased. So, x bar equal 13, 11, s equal 12, alpha equal 5%. 5%, alpha equal 5%. And the keyword here is increase. So very similar idea to the exercise 2. So we want to see whether modification of the computer batteries have been increasing life expectancy. So we want to test the hypothesis that mu is greater than 1305. Okay, this is prior. 1305 is prior modification of the battery, and now we want to see whether with the modification the population mean has increased over 1305. So is this corresponding to null or alternative hypothesis? Alternative hypothesis. Why? No equal sign, exactly, thank you. So therefore, null hypothesis would be what this is not. So it's mu less than or equal to 1305. So this is step 1. Step 2, alpha. 5%. Is this upper tail, lower tail, two-sided? What is it? Upper tail. Why? Okay, so it's greater than. So this is the direction of inequality points to the right, to the upper tail. So it's upper tail one-sided. Okay, so step 2, alpha 5%. Therefore, T of one-sided and alpha of 5% or 1 minus alpha of 95% confidence. And degrees of freedom, how many degrees of freedom do I have? 19. 20 minus 1. Okay. Then you look in the T table. You go to T table, concentrate on row 19, and then intersection of row 19 and column 95% one-sided is going to be our T value, our critical value, which is 1.729. 1.729. Is there anybody who cannot find this 1.729 on the T table? Everybody can find it? Okay. So this is critical value, one critical value. If we have upper tail or lower tail, then one critical value. Upper tail will be positive, lower tail will be negative. If it's a two-tail test, it's going to be two critical values, one positive, one negative. Okay. And step 3, test statistic equal x bar, which is 1311 minus mu naught. Mu naught is value of mu under null hypothesis, which is 1305, divided by s instead of sigma. We don't know sigma, so we use the best estimate of sigma, which is s, 12 over square root of 20, and that will give us the value of 2.24. Okay. Step 4, step 1, step 2, step 3, step 4 would be decision-making rule. Okay. So here we have T, and here we have a critical value of 1.729. Okay. And it happened that test statistic is 2.24. Test statistic 2.24. Now, for this type of test, we're going to have only two regions here. There's acceptance region to the left, and rejection region to the right. Okay, so we say that do not reject null hypothesis if test statistic falls in acceptance region, which means that it's less than or equal to 1.729. Otherwise, reject it. So where does the test statistic fall? In which region? Rejection. So conclusion, reject null hypothesis. So that's a statistical term. Rejecting null hypothesis means that we are rejecting this and we are maintaining this one. We're maintaining alternative hypothesis. So the conclusion is that we are 95% confident. There's 95% confidence that modification of the battery increased its life expectancy beyond 1305. That's the conclusion. So by maintaining this alternative hypothesis, in English, we say we are 95% confident that modification of the battery increased its life expectancy beyond 1305. We're going to maintain this hypothesis. We're going to reject this one. Okay. So in order to calculate p-value, it's a little bit more involved here. P-value, what you do is that you go to the table, T-table, and concentrate on row 19. So here, row 19, degrees of freedom 19, and you concentrate and then locate this test statistic, which is 2.24, locate this one between, if you can locate it exactly, fine. If you cannot locate it exactly, then find the two values that this falls in between. So go to T-table, and then concentrate on row 19, and so it's going to be between 2.093 and 2.593. So here, this is going to be 2.539 and 2.019. Okay. 93. Okay. So here, test statistic will fall. Then with your two fingers, once you find this one, with your two fingers, go up, because this is one-sided, go to one-sided row on top. And on one-sided here, because the test is one-sided, so here is, I believe, 97.5%, and here is 99%. Okay, everybody sees that? Okay. Okay, so 97.5 confidence corresponds to alpha of 2.5%. And confidence of 99% corresponds to alpha of 1%. So what you say is that p-value in this case is going to be in between 2.5% and 1%. We don't need to find exact value, but you can find exact value by interpolation if you are interested to find exact value. So that's how we calculate p-value when the t is involved here. Okay? I think they're 1 o'clock and they're going to, 2 o'clock, they're going to close. the building. So, is there any question? Everybody, I want to appreciate, I want to thank you for taking your time on Sunday. I know it's difficult coming here. So please call me, email me, text me if you have questions.